This is the third screencast for Chapter 2, and the subject of this screencast is radioactivity. So first we're going to look at natural radioactive decay. We're not talking here about nuclear power plants. So let's define radioactive decay. It's the spontaneous release of material from the nucleus of an unstable isotope. Okay, so let's go back and recap what the definition of nucleus was. That's the protons and neutrons that make up the core and most of the mass of a particular element. And in this case of uranium, the 92 indicates the number of protons here in this element. And you can see that the total atomic mass is much larger than 2 times 92. That's because it has a lot of extra neutrons. And therefore, since it has a lot of extra neutrons, it makes it an isotope. And it's very unstable. It's very large, both in terms of its just total number of protons, and it's very large because of the amount of neutrons in there. And you can imagine, if I think of a room full of people who are all very positive people. This is not a direct analogy, but hopefully it will help you. If you had a room full of people who were all very positive, maybe a little too positive, and didn't have enough neutrons in there, enough neutral people to balance them, they would repel each other, right? So a similar concept, but not exactly, is going on here. So this large unstable isotope decays spontaneously, and when it does, it changes from the original radioactive element, in this case uranium, into a different element or more than one element. So in the case of uranium, it spontaneously decays into helium and thorium. The uranium is called the parent, the thorium and helium are the daughters. Now again, this is happening naturally and spontaneously. And when it does happen, uranium or any other radioactive element doesn't spontaneously change into any other elements. It doesn't turn into gold or silver, anything like that, or even carbon. It always follows the same pathway. So uranium will always decay to thorium and helium. Now, in a nuclear reactor, what happens is an extra neutron typically is bombarded at the uranium, and that causes it to undergo a non-spontaneous chain reaction. Okay, so one aspect of radioactivity that needs to be carefully considered is its half-life. That is the amount of time that it takes for 1/2 of the original radioactive parent atoms to decay. And my example of how that works will be on the next slide. But the reason it's important to know is that many of these elements that undergo radioactive decay emit radiation that's harmful to living things. So back in the case of the uranium producing a daughter cell of thorium, thorium is also radioactive. So we want to know how long the element is going to stay in the environment and how long its daughter elements, if they are radioactive, will stay in the environment. Okay, so let's look at the next slide and explain how half-life works. So, if we have an atom that it's a radioactive atom, and it has a half-life of 10 years, then at time 0, our starting point, let's say that we had 400 atoms of this particular element and it had a half-life of 10 years. That would mean that 10 years after our initial time period where we had 400 atoms, we would then have 200 atoms left. Now, here's the tricky part. Think about what happens 10 years after that, or 20 years from time 0. Does that bring us down to 0? No, it does not. So after another 10 years elapse, Still, this 200 starting atoms that we have, only half of those have decayed. And so forth. So after 30 years, we still have 50. So it's similar to the concept in football of a penalty of half the distance to the goal. So if you are at the 20-yard line and the other team receives a penalty, half the distance to the goal, your team gets to move to the 10-yard line. If the other team then gets another penalty and you're at the 10-yard line at this point, you don't get to score. You don't get a touchdown. You only get to move again half that distance or down to the 5-yard line, etc., etc. So why is this important? Whoops. Okay, I'm going to pause it here because my slide did not behave properly, so hold on for 1 second. So knowing a radioactive atom's half-life is important because many times the elements that are produced, or many of the elements that are produced during the decay of uranium-235 have half-lives of tens of thousands of years. Think about that, tens of thousands of years. And that's just to decrease the amount available or present in half, not to remove all of it. Okay, so next we're going to move away from the idea of radioactivity and look specifically at how atoms form bonds with other atoms. And the bonds in general the bonding is called chemical bonds, and there are several main types. I'll go through and define them, and I also have additional examples on the next page. Okay, so the first and very common type of bond is called a covalent bonds. Valence refers to these orbits where the electrons exist and orbit. Co means share, like cooperate, cohabitate. So covalent bonds are bonds where the electrons in either element's orbit is shared equally with the other element. In the case of hydrogen, hydrogen has 1 proton and 1 electron, okay? So it equally shares, that electron, if you will, spends just as much time with the hydrogen atom as it does with the oxygen atom. Joint custody, if you will. And examples of this, here, this example right here is methane. 1 carbon and 4 hydrogen atoms. So you see the carbon in black here, and you see 1, 2, 3, 4 hydrogen atoms in a gray. And this is a molecule that we will discuss a number of times because methane is natural gas, and natural gas is a greenhouse gas, and well, we'll talk about it several times, especially about climate change. The little diagram here on the right is to point out the fact that covalent bonds and the way these elements are arranged, it's not a flat structure shown here. It's really a 3-dimensional structure. And we can look at that in class when we work with molecular models. Okay, so those are covalent bonds. Another type of bond is ionic bond. Remember, ion means the charged particles. So electrons are transferred from one element to the other. So you could have an example of sodium chloride. Sodium is Na, chloride is Cl. Chlorine is Cl, and then you put them together and it's known as sodium chloride, which is also just salt. And let's take a look on the next slide at how an ionic bond might be structured. So here we have the sodium on the left. It has 11 protons and 11 electrons. Chlorine is on the right. It has 17 protons and 17 electrons. But when sodium interacts with chlorine, one of the electrons that's all by its lonesome in this orbit here, in this shell, so it doesn't like to be by its lonesome. Notice how a lot of them, they're all here in pairs. So this electron then moves into the orbit of the chlorine so that this shell is filled and this one is completely empty. And then you get, since it's lost its electron, the sodium has gained a positive charge because it's down to 10 electrons. And chlorine has gained a negative charge because now it has an extra electron. So that is an ionic bond. Now we're going to look at another type of covalent bond, which is called a hydrogen bond. Now that I look at it, perhaps I should have put hydrogen bonds under covalent bonds. But it's a very specific type. So a hydrogen bond forms when there's a weak chemical bond between hydrogen atoms that are covalently bonded to one atom but are attracted to another atom on a different molecule. That sounds more complicated than it is. Let's look at a hydrogen bond. Excuse me. So hydrogen bond is between two different molecules, not within a particular atom. And we show here on the top a water molecule. So here's the oxygen in red and the two hydrogen atoms in gray. Each hydrogen atom has one electron, and it's sharing its orbit covalently with the oxygen. And same with the oxygen extra electron, sharing it covalently with the hydrogen. But when it does, it's slightly more attracted to the oxygen, spending a little more closeness with the oxygen than it is with the hydrogen. And that gives the hydrogen a slight positive, the hydrogen a slight positive charge here, and the oxygen atom a slight negative charge here. Now, if we put this water molecule together with other water molecules, the slight positive charge here on the hydrogen is attracted to the slight negative charge on the oxygen. And the slight negative charge on this oxygen also attracts the slight positive charge on this hydrogen. And therefore, the molecules, the atoms rather, sort of line up in basically a lattice type structure. It's not just any random structure. And that gives water some unique properties. I'll go through that on the next screencast.